Yes. Yeah. So just like, yeah, we took a midterm last semester in 410. So. I mean, yeah, it would be the same style of study guide. So yeah, I'll put it out next week.
Okay.
Yep.
Like would there be the problems to solve out?
No, it'll just be the learning objective. So the problems that you would practice are from the homeworks, mostly from homeworks 2 and 3.
So math will not be.
No. So basically what I'm expecting to do on the midterm is to take a differential equation and then discretize it using finite differences and then give me the like recurrence relationship. And so maybe I'll say like, maybe you have 5 nodes on this domain. So give me the 5 equations that you would solve.
Is there anything separate that you accept those?
Yeah. I mean, the homework 2 has quite a lot of those. Homework 3 you'll see more of those too.
So everything is just
Yes. Yeah. No computers. Yeah.
And then like obviously the conceptual stuff. Right?
Yeah.
All of the carbon copies that? Right. Is it the first?
So
Thanks.
It's like so there, like, nice. Oh, yeah.
All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Doing good, Good. All right, so it's our first meeting this week because we had the day off on Monday. So hopefully everyone had a good long weekend, right? All right, so the plan for today is, there's kind of 2 parts, 2 things I want to do today. So the first thing, I think last time we kind of left off on a little bit of a cliffhanger. And so we were talking about implementing a 2D diffusion code using finite differences in MATLAB. Okay? So we started that a little bit, but I wanted to kind of continue it and kind of go over it in a bit more detail, just so that you guys are more better equipped for the homework. Okay? And so I want to spend maybe the first 20-30 minutes on that. And then after that, we'll go ahead and move on to the next topic, which is convection. Okay. All right, so remember the homework. Homework 2 is due pretty soon. I believe it's due this Friday. And so I know a lot of you are waiting for today's lecture to do the last part of the homework, problem 3. And so hopefully after today, you should be able to do the 2D stuff. Okay. All right, let me just make sure the audio is on. Okay. All right, are there any questions I can answer before we get started for today? Yes.
Just a quick question. I know we have to do it by hand. We almost the exact same process, like the example, like 6x, or because of that problem, like it's had to figure out we have to go somewhere different.
It's mostly similar. I mean, yeah, I mean, because it's just a diffusion problem, I don't think there's any, I think the coefficients are mostly constant except for the right-hand side. So, the process would be mostly the same. I wouldn't like to still see the work in the homework. So I wouldn't like to see, take the original differential equation, plug in the finite difference, approximation and then work through that. But yeah, it would be mostly the same. I think the only thing that would be different are just the boundary conditions and just the right-hand side. Yeah. Any other questions before we begin? Okay, all right, so let's pick up where we left off last time. So last time we were talking about 2D diffusion. With finite differences. Okay. And so before we kind of jump back in the code, I kind of want to kind of go back to a certain point, just because, I know this part can be kind of confusing, and I try to take my time each year with the 2D diffusion because conceptually it can be a bit challenging. Okay? So remember what we're doing, or what our goal in this section, and basically every section in this class, is we're solving our conservation equation, right? Right now, our conservation equation only has one main term, which is diffusion and source, but we want to solve for a solution to that differential equation. Okay? So in essence, one form of the 2D diffusion equation looks something like this. And so we have a second order derivative in X, a second order derivative in Y, and we have some source term Q, which is XY. Okay. And so we want to solve this. Okay. And conceptually, you can think of this problem solving process kind of in 3 steps, right? So here's our equation. Right? We want to solve this equation on a certain domain. Okay. So our domain, most of our 2D problems is just going to be a square. Okay. Okay, so this is our domain. Okay. Whenever we have a differential equation, we have to have our domain. That's where we're going to solve it. Okay. And when I say that we want to solve for a solution, what I mean by that is we want to solve for the value of phi at every node in this domain. Okay. Okay. And so basically at all the nodes in the grid here, I'm not going to draw all of them because it's a bit too much. We're going to solve for a certain value of phi, right? So down here, that would be node 1. So we'd have phi1, that would be phi2, phi3, phi4, phi5. Okay. And so one way that you can think of it is that, depending on how many nodes are in the grid, that's how many solutions that we're going to get. Okay. So if our domain has 10 nodes in total, we want to solve for 10 solutions. Okay. Right. But if our domain has 100 nodes, then we're solving for 100 solutions. Okay. And so conceptually, we know that by applying finite differences, the way we're going to solve for each of these solutions is to set up a system of equations. Okay. And so what we're looking for is basically one equation, or what we're going to get is one equation for every node in the domain. Okay. And so if you remember from last time, we had a situation like this where we went from our domain, and what we said is that for each node, okay, so let's say that this is I is equal to 1. Okay. Or I should say node 1. I don't want to confuse you guys because we're in 2D, so we have both I and j. Okay. So I'll call this node 1. Okay. So for node 1, we're going to have some equation. So we'll have, phi1, maybe, plus phi2, plus da, da, da. Okay. Then we'll have another equation, say for node 2. Okay. And so on and so forth. Okay. This is what we want. We want one equation for each node because, if we have one equation for each node, then what we can do is we can solve that linear system together for all the nodal solutions at the same time. Okay? And you really have two options here, the equations are going to come from one or two different sources. Okay? And so in the first case where you have an interior node, in the interior node, what we solve or how we obtain our equation is from the governing finite difference equation. Okay? The other option that we have, or the other source of equations that we have, is if our node is resting on a boundary. Okay, so if the node is on one of the boundaries of the domain, then we're going to obtain our equation through the boundary conditions. Okay. So whether you have an interior node or a boundary node, you're going to have an equation for each node. Okay. What we do from here to make it easier to solve is we take our linear system equations and we put it in matrix form. This is the part that confuses people because when we're building our matrix, especially in code, the matrix doesn't, there's not a direct correlation to the domain. Because I think what some people seem to think, and I get questions on this every year, and this year I got like 4 people asking me this, okay, is that when we're constructing our left-hand side matrix, this entry in the matrix, maybe in the top left, does not necessarily mean or does not necessarily correlate to the top left-hand side of the domain. Okay, the matrix represents the system of equations. It doesn't necessarily have any correlation to the physical locations in the domain. Okay, so that's kind of one thing that's I know it's going to be it's going to take a while. I can say that at the beginning of the lecture every day for the next 3 weeks, but I think it's one thing that takes a while to kind of sink in. Just remember the matrix form is just our representation of the algebraic set of equations. Okay? In terms of terminology, this is the left-hand side matrix or LHS matrix. And this right here is our right-hand side vector. Okay. Right, so conceptually, the terms in our left-hand side matrix or the entries in that matrix, those are going to be the coefficients in front of the phi values from the previous step. Okay. And so that's why you'll always see our left-hand side matrix typically follows a certain pattern, right? And so it always follows the 1, -2, 1 pattern, because by implementing the finite difference equation on the interior nodes, we just kind of naturally end up with that pattern based on the pattern of the finite difference scheme that we're choosing, okay? All right, and so what we're doing in the code is that, we kind of know this process. And so conceptually, we know this is the process we're going to take. The most efficient way to write our code is to just directly specify or directly assign or directly build up these matrices. Okay. Okay. I think that, one thing that people realize in this class, and I get comments like this all the time at the end of this class, that there's quite a significant kind of theoretical component, right? It's the method that we use is very different than maybe kind of what you're accustomed to, maybe if you took finite elements last semester or anything like that. Okay? You have to really kind of work on the theory of the problem first, get the finite difference equation, get the equations for the boundary conditions, and then implement those in the code. Okay, and so you can't, a lot of times you can't just start writing the code immediately. You have to do a little bit of work on paper first so that you know exactly what equations or what expressions to actually implement in the code. Okay, but I wanted to kind of highlight this because, I think once you start getting into the weeds and once you start getting into the nitty-gritty details of writing the code, it's kind of easy to forget kind of why we're doing each step and where each step kind of comes from. Okay, and especially for 2D problems where we have the 2D domain, which kind of looks like a matrix, I want to kind of make sure that everyone kind of knows where each part's coming from. Okay. All right, any questions on this? Okay, all right, so let's jump back in the code. So let me go ahead and share my screen. Okay, so what I have open right here is this is the starter code. So if you go to Canvas site, I've uploaded a code here called EGME 417 2D diffusion finite difference starter.m. Okay, and I believe we were starting to work on this code from last time. Okay. All right, and so what I wanted to do today, I think we went over it kind of slowly last time as well, but I wanted to make sure that we kind of went over in detail today so that you kind of know what to do. All right, so let's start with section 2. If you read section 2 here, you can say section 2, what we're going to do is we're going to populate the left-hand side matrix with the finite difference formula for all of the interior nodes. Okay. All right. And so just like I showed you in the graphic before, what we're doing is we're filling out the equations for all of the interior nodes. Okay. And so to do this, I'm going to write a nested for loop. Okay. All right. Because to write an equation for all of the interior nodes, we should visit all of the interior nodes, right? And so if you remember from our MATLAB practice, the best way to do that for a 2D structure is to just have a nested for loop. Okay. All right. And so the way you can think of this is that, we're going to be building up this matrix one row at a time. Okay. So each iteration of this loop will focus on building one row of the side matrix. Okay. All right. So first thing we need to do is we need to get the proper ID numbers for this node, right? Because right now what we're looping over is we're looping over ij, but in order to get the appropriate row in the matrix, we need to know its ID. Okay. So let's first compute our ID number. Okay. And so our ID equation, if you remember from last time, was nx times j minus 1 plus I. Okay. Not only do we need this, we also need the ID numbers for all of our neighboring nodes as well, right? So remember, the part of the finite difference equation for the 2D diffusion is that we need to take information from all our neighbors. Okay? And so we have left ID, right ID, top ID, and bot ID. Okay? So these are going to be all the ID numbers for all of the neighbors for this node. Okay? Nx times j minus 1. If we're going to the left, we're going to have an I value that's 1 less. And if we're going to the right, we're going to have an I value that's 1 more. If we're going up top, our top neighbor has a j value that's 1 greater than the one that we have. Okay? So it's going to be nx times j plus I. And if we're going 1 bottom, we're going to have a j value that's 1 less. Okay? So it's nx times j minus 2 plus I. Okay. All right. So now that we have the ID numbers, we need to set the proper coefficients for each of these terms. Okay. Okay. And the way that we do that, we need to make the left-hand side matrix. Let me do this real quick. Okay. Let's do left-hand side matrix. Let's do the diagonal entry first. So the diagonal entry will be ID comma ID. Okay. And if you remember from our finite difference equation for the 2D diffusion, this has a coefficient of -4. Okay. Right. And then for all the neighboring nodes, we're going to have a coefficient of 1. Okay. Notice how, in all of these specifications for LHS matrix, the first entry here is always ID, right? Because remember, we're building up this matrix one row at a time. And so, when we're, while we're still in kind of the same iteration of the loop, we should still be working on that same row. Okay, so that's why ID doesn't change here. What changes here is the column. All right, and so if we do that, that should set all the coefficients that we need to for this part of the code. Any questions on this? Okay. All right. So I do want to make kind of one small change to this. Okay. Notice how this is for all of the interior nodes. Okay. So let me go ahead and draw the domain here again. And so all the interior nodes would be the nodes kind of on the inside of it, right? And so it would be all of these ones. Okay. Remember, for the boundary nodes, or the nodes that are sitting on the boundary, we want to apply boundary conditions on those ones. And so those ones aren't going to be, we're not going to apply the interior node equation for those ones. Okay. And so what's interesting about this kind of this inner ring right here is that, we don't have to start at 1 and go to NX, right? Because if you look at this, the coordinates for this one right here, this is going to have coordinates of 2, 2, right? Whereas in the top right here, this is going to have coordinates of nx -1, comma, ny -1. Okay. And so those are the only nodes that we should apply this to. And so we should adjust our loop accordingly. And so instead of doing for I is equal to 1 to nx, we can set the loop to start at 2 instead, and then go to nx -1. Okay, and same thing for j. So for j, we're going to go from 2 to ny -1. Does that make sense? Any questions on why we adjusted the loop bounds for that? Okay. So that's all the interior nodes. So actually, that's the bulk of the nodes. So actually, we've already done most of the nodes here. Okay. The only things left is that we have to apply our forcing function, and we also have to apply our boundary conditions. Okay. And so is there a way to make an if statement in the case our mesh isn't a square? That's a great question. So, a lot of, the way I've structured this code really relies on the fact that our mesh is a square. If you don't have a square, you have to, a lot of times you use a different kind of data structure. So you use kind of a connectivity matrix. And so, instead of having this explicit equation right here for the ID number, what you would do is that you would assign the ID number separately and then keep track of it in a separate vector. Yeah, so that's a pretty traditional way to do it, especially for things like finite elements where you have kind of a very complex mesh besides that. And so, for a more typical case, you have kind of a more sophisticated way to do the ID number. So that's typically how you do it. Yeah, we might get into that. I might change up the final project to do something like that, but I'm still kind of deciding. But yeah, that's how you would do it in kind of a generic case. Okay. All right, so let's do the forcing function now. And so our forcing function in this example is 3xy. Okay. So this should be applied in the RHS vector. Okay. Right. Basically, if you look at your original equation, any term that doesn't have a phi inside it or does not a function of phi, that should go in the right-hand side vector. Okay. And so whenever you have a source term or you never have a forcing function, it always kind of appears in that right-hand side vector. So what I'm going to do is I'm going to make another loop here. This one I'm going to loop over all the nodes because the forcing function applies to all the nodes. Okay. And what we want to do is we want to make a specification or a change to the right-hand side vector, which I think I need to write up here. I think today I didn't compared to last Wednesday. I think we wrote a lot of extra variables up here. So make sure you take note of that. Just in the interest of time, I'm going to skip to the sections that I didn't have enough time to cover last time. But make sure that you have all those extra variables because you do need them for this problem. Okay, and so what we're going to do in this section is basically we're going to assign a value to the right-hand side vector according to our source function. All right, and so just like the last loop, we're going to need a formula for the ID. Okay, so actually I'm going to go ahead and copy and paste that from up here. So that's going to be the same. And so we need to implement the function 3 times x times y. Okay, where x and y here, I should say x comma y, are the physical coordinates for this ij node. Okay. And so in order to compute x and y, we need to take the grid spacing into account. Okay. So I'm going to create new variables here. So I'll call this x position and y position. And so these are variables that are going to basically have the x and y positions of this node. Okay. And to do this, it's actually quite simple to compute. And so what you're going to do is you're going to take the grid spacing in the x direction, multiplied by I minus 1. Okay. And then you're going to take the grid spacing in the y direction, and then multiply that by j minus 1 for y position. Okay. Right. So the reason we do this, remember, is that the I and j coordinates, those are kind of more numbering. Okay, it's more of a numbering coordinate system more so than a physical coordinate. And so to get the physical coordinate, you have to multiply basically the numbering coordinate by the grid spacing. Okay. And so under this scheme right here, basically the node that's in the bottom left with a value of I, j is equal to 1, that should be 0, 0. That's your origin. Okay. And then as you get away further from the origin, this will compute, what are the x and y coordinates. Okay. So now that we have these x pos and y pos vectors, so let me go ahead and change these in here. Okay. And so to implement the forcing function or the source function 3 times x times y, you would do 3 times x pos times y pos, where x pos and y pos are given by these variables here. need to do one more thing. Because of the finite difference equation, we also have to multiply this by dx times dx. And so this part right here, probably in your notes, if you kind of go back in your notes, this dx times dx is basically delta squared. And so that delta squared came directly out of the finite difference equation for this. Okay. All right. Any questions on this? Yeah. Yes. What I can do after this, I know all I have is the starter code online. I think I have the finished code on there as well. It's just in the codes folder. I'll have to look for it. But I can also post the code that we're working on in class today so that you can use that for the homework. The reason I'm kind of going through this is that, you're going to be writing a lot of codes like this, especially I think for problem 2C. And so it's kind of important to know what each section does, so you know how to write. Okay. I will tell you, I'll give you a big hint right now. So when you do problem 3C on the homework, I think it's 3C. A lot of the code for 3C is going to be the same for this code. So I will tell you that, section 2 of 3C will be exactly the same because it's basically the same equation. Okay. Section 3 will be a bit different because the source function is different and the boundary conditions will be slightly different as well. Okay. But try to see which parts are going to be the same for problem 3C versus 3A, where 3A is just kind of a repeat of this. Okay. All right, any other questions on section 3 of the code? Okay. All right, so now we come to the boundary conditions. Okay, so you can see I've created a section for each of the boundary conditions. Remember, each of the boundaries are going to have its own separate boundary condition, right? So we have section 4 here. So section 4 applies the boundary condition on the left boundary where I is equal to 1. Section 5 applies the boundary condition on the top boundary where j is equal to ny. Section 6 applies the boundary condition on the right where I is equal to nx. And section 7 applies the boundary condition on the bottom where j is equal to 1. Okay. I'm just going to do a couple of the sections here and show you how to do them. I'm going to do one example of I should have changed this, but this is an example of a Dirichlet boundary condition. Okay. And section 5 is a example of a Neumann condition. So I'll do parts 4 and 5 of the code. And then what you can do is you can kind of take those, take that code and apply it to section 6 and 7 as well. Okay. Okay, so let's do section 4 first. This one's a little bit easier. Okay, so we have a Dirichlet boundary condition. It's applied on the left boundary. Okay? If you remember from last lecture, when you have a boundary condition in a 2D domain, you have to write a loop because the loop is going to visit every single node on that boundary edge. And so your loop is either going to loop over I or j. Or j, depending on which boundary. Okay. Excuse me. All right. And so for the left boundary, let me go ahead and draw the square again. The left boundary here is a vertical boundary, right? And so we know kind of from the hint here that for every node on the left boundary, the I value is equal to 1. Okay. But then we're going to go vertically up. Okay. So this tells us that our loop here is going to be in J, not in I. Okay. Because we need to traverse vertically in order to visit all of the nodes on the left. Okay. Let's do loop from 1 to n. Okay. All right, so first thing I'm going to do, usually is a good idea to do in a 2D problem is to compute your ID number. So I'm going to go ahead and copy our equation for the ID number down here. Okay. Because remember, whenever you're setting an equation or setting a value in the left-hand side matrix or right-hand side vector, we need the ID number to do it. Okay. I am going to make one change to this equation though, because normally we're doing nx times j minus 1 plus I. If we're on the left boundary, we know what I is going to be, right? So I here is going to be 1. And so instead of I, I'm just going to replace this with 1. Okay. And then the equation that we want to apply, remember, is a Dirichlet boundary condition is very simple. So for Dirichlet boundary condition, what we're saying is that phi at I, comma j is equal to phi naught, where this phi naught here, this is the prescribed value. Probably the best handwriting I've ever done with the mouse before in my life. Okay. All right, so why is this simple? Okay. So let me go back to the diagram so I know what boundary condition it is. Okay. So this is simple because this is basically going to constitute our entire equation, right? And so we're going to insert this equation into our matrix system. Okay. And so the left-hand side of this equation means that we just have one value here, right? And so this side basically means that we have a coefficient of 1. And that coefficient of 1 is going to be on the diagonal entry. Right, because remember we have phi I comma j, that's going to be the diagonal entry. Okay. So let's go ahead and do that first. And so in our code right here, okay, so let's do left-hand side matrix. It's going to be ID comma ID. And so this is going to be equal to 1. Okay. And then the other change that we have to make is going to be in the right-hand side vector. Okay, so I know maybe this this notation is a bit confusing here. Let me just write in the exact what the exact boundary condition is in this case. Okay, so for the left boundary, we have bi comma j is equal to 50. Okay, and so this 50 here, this is going to go directly into the right-hand side. So we put that in code. We have RHS vector at ID. Okay. We only have one coordinate for the RHS vector because it's just a 1D vector. And this is just going to be 50, just like that. Okay. And so that is the loop that you would write for the Dirichlet boundary on the left. Okay. So remember, first compute the ID numbers, then make the modifications to the left-hand side matrix, then make the modifications to the right-hand side vector. All right. Any questions on how we wrote that loop there?
Where did the 50 come from?
The 50 is from the problem, and so I had to look it up in the problem itself. And so the 50, because in every problem, basically, you're given for every 2D problem that I give you, I always give you a picture of the domain. And so in this case, the domain is a square. Okay. And then on each side of the domain, I give you the boundary condition. So for this particular example, I should have written it again, just to kind of jog your memory. But if you look back in your notes, on the left boundary, we have phi is equal to 50 on that side. Yeah. Let me go ahead and write in the rest of the boundary conditions here too. So on the bottom, we have phi is equal to 25. Right, we have partial phi. Oh, it's gonna be hard. Partial phi, partial n is equal to 0. And up top here, we have partial phi, partial n is equal to 10. Yeah. So this is given. This is always given to you. Yeah. You don't have to make up boundary conditions. And so your job is basically to take the given boundary conditions and implement them in the code. any other questions on this loop here? Okay, let me do an example of a Neumann boundary condition. So we'll do it on the one up top, and then I'll let you guys do the other two. Okay, so let me go ahead and clear this. Okay, so let's do the top boundary. So I'm going to do the same thing. So we're going to start with the loop. For the top boundary, it's going to be a little bit different. So for the top boundary, our fixed coordinate is going to be j, right? So j is going to be fixed at ny. And so we're going to loop over I instead. Okay, so I is equal to 1 by 1 to nx. Okay. First thing we're going to do is we're going to compute our ID number. So our ID number is going to be nx times j minus 1 plus I. Okay. The difference here is that we know what j is, and so we're not going to leave it as generic j. We know that j in this case is going to be equal to ny. So let's go ahead and plug that in. All right, and so let me pause here for a second before we start making any modifications. Okay. And so our boundary condition up top states that partial phi, excuse me, partial n is equal to 10. And so remember, the way that we incorporate this into the matrix is that we replace this with a finite difference expression. And so instead of partial phi partial n, we have phi inner minus phi boundary all divided by delta. And in this case, this is equal to 10, but you know, for most problems, you would replace this for whatever the boundary condition actually is. Okay. All right. So I'm going to multiply both sides by delta. And so the delta is going to be eliminated from this side. So we're going to have a delta over here. Okay. And we're left with this equation right here. So this is the equation you're going to input into the matrix set of equations. Okay. And so this tells us is that on the right-hand side, we're going to input a value of 10 times delta. So that's going to be 10 times dx. Okay. And then, as opposed to the Dirichlet boundary condition where we only had one modification to the left-hand side matrix, here we're going to have two modifications. Okay? So we're going to need a modification of the coefficient for phi inner, okay, as well as a coefficient for phi boundary as well. Okay. Okay. So phi boundary, this is the phi value that's sitting on the boundary condition. Okay. So this is actually going to be phi I comma j. Okay, so that's going to correspond to ID. Okay. So we have that one already. And so we need to find the ID number for the inner node. Okay. Okay. So actually, let me do this too. So for this particular example, we know it's not just phi I comma j. It's actually going to be phi I comma ny, right? Because j for the top boundary is ny. And so we want to go one direction on the interior. So instead of phi I comma j or phi I comma ny, okay, if we go one interior from the top, okay, and so we have, let me draw our domain again. Okay. And so if our top has a j value of ny, that means the row that's right underneath the top one, this one right here, this is going to be j is equal to ny minus 1. I was kind of a mess right now, but you know, it'll enter in the code. So, okay, so I'm going to compute a second ID. So I'm going to call this inner ID. Okay. And so inner ID is going to have a similar form as ID number up here. So let me go ahead and copy and paste this. Okay. But instead of just ny right here, okay, we're going to replace that with ny minus 1. Because that's the node on the interior. Okay, so we have ny minus 1 plus I. Okay. And of course, you can combine these. You don't have to do minus 1. You can just do minus 2. Okay. So now that we have the ID numbers, let's go ahead and make the modifications. Okay, so we'll do LHS matrix ID comma ID, and then LHS matrix ID comma inner ID. Okay. And let's have right-hand side vector and ID. Okay. All right, so let's do the coefficient for ID comma ID, right? So this is the diagonal term. So from this equation right here, you can see that the coefficient is going to be minus 1. Whereas the coefficient for inner ID, this is going to be 1, according to this equation right here. Because basically we're going to be incorporating this equation into the matrix. And then our value for RHS vector, it's just going to be 10 times dx. Okay. According to this equation, right? Right. Any questions on this?
Can you scroll to number 4 really quick?
Oh, someone on Zoom? Sorry, the audio is a bit low.
Can you scroll to 4 really quick?
Yes. Yeah, I'll post this code online just so you can see. I think I have the completed code online too. Let me just check and see real quick. Notes. I hate this in Canvas. It cuts the names off, but let's see. 2D diffusion should be this one. This one is a higher file size. Yeah. Okay. Yeah. So this one actually is the completed code. It actually has everything completed, even the other boundary conditions. But even then, you can look at this code. So let me go ahead and post it on this week's weekly page here. And so, if you're in a rush, you can use that to solve problem 3A. But I would definitely encourage you to try to fill in the last 2 sections yourself, just that you kind of know exactly what they are. Okay. But if you do want to check your answers and to kind of make sure that it's right, this is the completed code right here. So of course, there's 2 more sections to write here. And so if you're kind of following along in the class, you would have to fill in these 2. But everything else in the code should be written for you. So I've gone ahead and solved the solution, or I guess I could solve the solution here. So T solution. It's going to be same as a 1D problem. So we're going to have left-hand side matrix / right-hand side vector. Okay. That part's pretty easy, but then sections 9 and 10, I've already kind of done for you. So you don't have to modify sections 9 and 10. And so the only ones that you would have to fill in still are just 6 and 7. All right, so hopefully that's helpful. And so, I try to go through each section here, but definitely go through this again. I know, even with this, it still kind of flies by at 100 miles an hour when you're trying to type and kind of understand the code at the same time. So, definitely go back to this recording, definitely look back at the notes and kind of see where each parts of this code come from. Okay. Because from here on out, the codes are just going to get more and more complex. And so, I have these kind of coding days and I have these kind of coding workshops in the class so that, you kind of are kind of keeping up, because, if you, just kind of skip to the next section and just kind of start writing the codes from there, it's going to be a lot more, daunting. And so once we kind of whenever we introduce code in the class, it's always good to kind of go back to it and kind of make sure that you understand everything, just so that you're kind of keeping up with that part. So it's, it becomes easier. Okay. All right. But again, the completed code is posted online, so you can have that as well. So hopefully all that is useful. All right. Any final questions on this before we move on to the next topic? All right, so let's go ahead and go back to the notes. So let me go ahead and nice zebra. Okay. So that's enough code for today. And so, hopefully that's helpful for you in the homework, but let's talk about some theory again, because it's there's only so much coding you can do in one day. Okay, so our next topic in the course, and this is going to be the last topic that I cover before the midterm as well, is going to be convection in finite differences. Okay. All right, so far, we basically did all of diffusion. So we did diffusion, we started with diffusion problems in 1D, and then we did diffusion problems in 2D, okay? And so if you looked at all of our equations, our diffusion equations always had a second order derivative, okay? Okay, and so it looks something like this. And so in 1D, we had simply d squared phi dx squared, or in 2D, we had partial squared phi partial x squared plus partial squared phi partial y. Okay. And so all throughout the diffusion section, we focused mostly on just the mathematics, and we focused on the code, just because I think those are the two things that are kind of new. Okay. We didn't really talk too much about what diffusion kind of physically represents. Okay. Because if you remember, this class, as much as you might disagree with me up to this point, this class is an engineering class, right? So all of the equations that we're solving, they have a physical meaning behind them. Okay, and so diffusion, what it represents is diffusion is basically called, I call it, passive spreading. So what that means is that, diffusion is going to spread, or the way diffusion works is that it takes a quantity and it kind of spreads it equally in all directions, kind of slowly. Okay. So just to kind of give you a visual representation. Okay. So I think it's kind of best visualized in 2D. Okay. And so let's say that you have a 2D domain right here, and you have a some kind of concentration. So let's say you have a very hot object in the middle. Okay. And so let's say you have a situation where you have kind of a very concentrated hot object in an otherwise cool room. Okay. Over time, what do you expect to happen? Right? Over time, even if there's, let's pretend there's no airflow in the room at all. Okay. Over time, the presence of that hot object is going to start to heat the room, right? And so if someone brought in kind of a bucket of lava in this room, let's say, for instance, right? Over time, what we expect is that that bucket of lava is going to make the temperature in this room hotter. Okay? So what we can say is that temperature or heat is going to spread to the rest of the room. And it's going to spread in a manner such that, you know, the outer parts of the room are going to start to feel more hot, okay, like this. Okay. And so kind of the influence of that hot bucket of lava is going to spread to the other parts of the room. But also what's happening is that at the center where the bucket of lava used to be, that's not going to be as concentrated anymore, right? So, you know, you kind of start with a very concentrated section of heat in one area, and then that starts to kind of spread itself out to all the others, okay? And so you have kind of a situation like this where, you know, you have kind of a spreading of that thing. Instead of everything being concentrated at one point, you know, it all kind of spreads evenly throughout. Okay? And that's by diffusion. So that's basically what we've been doing, you know, up until this point. Okay? And mathematically, when you represent diffusion, it looks like it usually becomes a second order derivative. Okay. Okay. Convection, on the other hand, convection is what I like to call kind of forced spreading or forced transport. And so, you know, convection is similar to diffusion in a way, in that it represents kind of a transport of the quantity from one you know, part to another, or one location to another. It's just that the mechanism that it uses to transport is different. Okay. And so when I say forced transport, you know, we need kind of an agent. Of course, we need an agent that's going to force it, right? And so it doesn't force itself. Okay. And so the way that convection works is that you need a flowing fluid. So let me draw the same example. So let's say that we have a room here, and we have a concentration of heat in the middle. Well, what's different about this scenario here is that I'm going to introduce some airflow. So let's say that we have a fan, or let's say we have a window that's going to blow air from the left side of the room to the right. Okay. All right, so what's going to happen? And so, you know, let me go ahead and draw the room again. The room somehow grew. My poor drawing skills. And so, you know, just like the first example with diffusion, you know, we're going to have heat that's going to spread throughout the room, except now the distribution is going to look a little bit different, right? And so because of the presence of the airflow, you know, what do we expect? And so what we expect is that instead of the heat kind of spreading equally to all parts of the room, okay? So in diffusion, you know, it kind of looked like this, where the heat was kind of spreading to all parts like that. Okay? Instead of the heat kind of spreading all, you know, equally like that, now the air is going to take some of the heat with it, okay? And so now you have a situation where you have kind of a hot section of the room and a cold section of the room. But what's happening is that the air is kind of forcing that energy or forcing that heat to go to one side of the room. So that, of course, looks very different than, you know, our situation with just diffusion, where kind of every room, or every section of the room is getting heated kind of, or, you know, equally, depending on your distance from the heat source. Okay. All right, another thing that's a little bit hard to illustrate using just pictures like this is that this process of forced transport via convection, it often happens a lot faster than diffusion. Okay. All right. So, in this section, what we're going to do is that, we're going to be solving equations that have convection to it, okay? And so, we're going to go through different parts. So first of all, we're going to see, mathematically what this means. We're going to see, what computational techniques that we're going to use. And then we're going to see what effects that this has on our solutions, okay? But before we really get into it, and kind of a lot of the discussion that we're going to do, a lot of it hinges on this kind of physical understanding or physical, or at least I should say conceptual understanding of the difference between diffusion and convection. All right, any questions on any of this? Okay. All right, so mathematically, how do we represent convection? So convection mathematically is represented by first order derivative. So oftentimes it takes the following form. And so we're going to have u times d phi dx. So we'll start with 1D and then we'll go to 2D after that. Okay. And so the thing to note here, or the kind of the most important feature here, is u. Okay. So this u, this is our convection velocity. So this parameter that we're going to use in our equation, it tells us, how fast the fluid is flowing, how fast the airflow is going, but it's also going to tell us the direction. So depending on whether that convection velocity is positive or negative, that's going to tell us the direction. And that's actually going to be pretty important for when we do our finite differences, okay? Right. And so if we take this term, and we insert it into our equation, our governing equation now, or our conservation equation, takes the following form. Okay? And so I'm just going to stick to 1D for now. So we're going to do 1D first, and then we'll talk about 2D after that. Okay? And so our 1D equation looks like k d squared phi dx squared is equal to u d phi dx plus q. And so, of course, we have here our second order derivative. This is our diffusion term. We have u d phi dx. We just talked about this is convection. And q, of course, this is our source term. Okay. So now we're going to be solving all three of these together in our equation. All right. And so, of course, the main new thing here is that we have a new derivative that we're going to be discretizing. Okay. And so we're going to discretize this with finite differences, just like we did before. We have kind of an interesting decision ahead of us, right? And so if you recall from a couple of weeks ago, when we have a first order derivative, we actually have three different options for the finite difference. Okay? And so we had kind of the classical central difference. We had forward difference. And we had backward difference. Okay. And all we've talked about so far is just kind of the relative accuracy of each of these techniques, right? So we know that central difference here is second order accurate, whereas forward difference and backward difference is only first order accurate. Okay. So just from a purely accuracy or from a purely kind of numerical error perspective, you know, it seems like the best choice is going to be central difference. Okay. Because remember, we always want to maximize our order of accuracy. And so, you know, from that perspective, it usually doesn't make that much sense to use either forward difference or backward difference because we know that those are going to be less accurate. Okay. But of course, you know, the reason I'm bringing this up is that, you know, maybe there is a reason why you might use forward difference or backward difference. Okay. And you know, spoiler alert, there is a difference. There is a reason. Okay. And so in convection, this is a good time to talk about kind of another important issue in all of computational science, not just finite differences, which is stability. Okay. And so before you can even start talking about accuracy, you know, you need to make sure that your solutions are stable. Okay. And so we'll talk about, you know, what stability is, what instability is, you know, how you can kind of, you know, what it looks like, why it's bad or why it's good, and then, you know, how to kind of guard against it. All right. Any questions on this? Is stability the same as steady and unsteady? It is not. So it is different. Yeah. So stability is referring to something different rather than steady state or unsteady. Okay. All right. So we have about 10 minutes left. And so I think the last thing we'll do today is kind of talk about that decision. Okay. So let's talk about finite difference schemes for convection. Okay. So, you know, like I just mentioned, you know, we have three different decisions or three different choices that we can choose for our first order derivative. Okay. For diffusion, it wasn't really a decision. We had one option for diffusion, and that was our central difference scheme. Okay. Okay. And so for diffusion, we had d squared phi dx squared. Okay. That was the scheme that we used for diffusion. So we had phi I plus 1 minus 2 phi I plus phi I minus 1 all over delta x squared. Okay. Let's look at this in kind of a different light. And so let's look at the coefficients in front of each of these phi terms. Okay. And then let's kind of put it onto a line right here. Okay. Okay. Excuse me. All right, so what I've drawn on the right there is basically just a number line representation of the nodes, okay? And what I'm gonna put over each of these nodes is I'm gonna put kind of the weight that is brought about by the finite difference scheme, okay? And so for phi I, we have a weight of -2. Okay. I'm gonna ignore, I know there's a divide by delta x squared, but you know, I'm just gonna ignore it for now. Okay. For I plus 1, we're gonna have a weight of 1. And for I minus 1, we're also going to have a weight of 1. So that just comes directly from the finite difference scheme. Okay. All right, and so if you look at this diagram right here, and if you almost look at it like a seesaw, right? So let's say that, you know, we have a hinge right here, and it's hinged right at phi I. this seesaw here is perfectly balanced, right? So we have a weight of 1 each on the left and right, and we have a weight of -2 on right on the hinge. Okay, so this is perfectly balanced, as all things should be, right? I know that joke's getting old because, you know, Avengers is an old movie now, but I could tell my inner mind was like, say the thing. But, you know, so I said the thing. It was weird. On Saturday, I went to hang out with some of my high school friends, and I went to a really nerdy high school. And so, you know, it was the first time I saw a lot of these friends in a while. And of course, what do a bunch of nerds do when they get together? They try to learn something. So they looked up my lectures on YouTube and they started watching them. I was like, what? Come on, man. We're sitting here drinking mimosas and watching my lectures on finite elements. Like, come on, let's do something else, guys. All right. Anyway, okay. So it's perfectly balanced, right? And that makes sense because if we kind of scroll back up here, right? And if we think about what diffusion kind of physically represents, it makes sense, right? So the way diffusion works is that it's kind of an equal spreading in all directions, right? And so it doesn't really have a directional preference. So, you know, once you have something in diffusion, it just kind of spreads in all directions equally, okay? And so when you look at the finite difference scheme, the finite difference scheme represents this almost perfectly, right? And so because diffusion is kind of equal spreading in all directions, it makes sense that our finite difference scheme is also going to be equal in weight in all directions as well, right? So there's no preference on left or right here. You know, it's all kind of the same. Okay. And so what we can say is that this scheme matches our kind of the physical process, you know, pretty closely. Okay. So let's look at convection. Okay. Let me start with the central difference scheme. I think that's kind of the first intuitively, that's what you would think the first thing you would do. So you use central difference because you know it's more accurate, right? So we have phi I plus 1 minus 2 phi I minus 1 all divided by 2 delta x. Right. So I'm going to do the same thing. So I'm going to draw a number line here. We're going to have I in the middle, I plus 1 on the right, I minus 1 on the left. Okay. And just like before, or just like in diffusion, I'm going to draw the weights from the finite difference scheme. And so we're going to have a positive 1 on I plus 1 and a minus 1 on I minus 1. Okay. For now, what I'm going to do is I'm just going to ignore the negative sign here. Okay. So we're just basically looking at absolute values. Okay. And so you can see here that we have a 1 on the left and a 1 on the right. And so just like diffusion, we have a scheme here that's balanced on both sides. Okay. And so you can see why, you know, this scheme here is more accurate because it kind of, you know, it's balanced. And so, you know, when you compute the derivative with it, you take information kind of equally from the left and equally from the right. And so that kind of cancels out some of the errors and then you get something that's more accurate. Okay. But unlike diffusion, you know, convection fundamentally is a different process than diffusion, right? And the way convection is different is that one way we can say that convection is different is that it has a preferred direction. Okay. right? And that preferred direction is the direction in which the fluid is flowing. And so, if we have a case where the fluid is going from left to right, what we can say, another way that we can say this is that information is traveling from the left to the right. Okay. And so from that sense, the fact that, convection has a preferred direction, it's not like diffusion, which spreads equally in all directions. It makes a lot of sense that we have a different scheme, or we have a different scheme that's going to fit this better. Okay. Because kind of a theme that's in a lot of computational physics is that, when you choose a scheme, and there's literally hundreds of different computational schemes out there, usually the ones that work the best are the ones that kind of match your physics as closely as possible. Okay. So for diffusion, we've already seen that. So for diffusion, we've already picked a scheme that matches that phenomenon pretty well. So for convection, we want to do the same thing. Okay. And so for convection, we have a technique known as upwinding. And the idea with upwinding schemes is that, you choose a scheme that's going to place more weight or more kind of coefficients on the upstream side of the fluid flow. Okay. And the reason for this is because that's where the information is coming from, or that's where the fluid is coming from. And so very last thing, before we end class today, is that if we were to apply an upwinding scheme on this particular fluid, okay, so let's say that we have a fluid that's going from left to right, okay, we would want a convection scheme, or we want to find a different scheme that places more weight on the left side. We want more weight that's on the left side because that's where the fluid's coming from. If we put weight on the right side where the fluid is going to, physically that doesn't really make that much sense because that's kind of the different direction that the fluid is going. Okay, and so for a fluid that goes from left to right in this case, the proper upwinding scheme would actually be backward difference. Okay, and so what we'll do on Monday is that I'll show you if you use a backward difference in this scenario, you're actually going to end up with a more stable solution. Okay? It may not be as accurate as central difference, but accuracy doesn't really matter if you're unstable. So I'll show you kind of what that means on Monday. Okay? All right, so thank you guys for coming today. Hopefully the MATLAB part today was useful for your homework. But if you have any other questions on it, you can definitely still reach me. So I'll be available through email kind of all day tomorrow. I have office hours from 10 to 11 tomorrow, so you can stop by then as well. Because I know, it's kind of our first kind of major, this homework 2 is the first kind of major MATLAB part. So, I want to make sure that everyone is kind of knows what the gist is. Okay, so please don't be afraid to reach out. Friday, I'll be available as well. So, definitely comment as well. All right, so thank you guys for coming today. Thanks for staying a bit late. And hope you guys have a good weekend, and I will see you on Monday.
Any update on the?
I signed the forms and I sent them back to Kevin. I think he's probably just getting them signed by, because it has to be signed by our department chair as well as the associate. So I think.
And also one more thing, so I was checking out the date, it said that the second assignment has been drawn for the final calculation. Why is that?
So the, I've set up Canvas site so that the lowest homework grade is dropped. And so,
Everything is like 100, so.
yeah, so I mean, it just drops one by default. So if you have 100 by on everything, then it just drops. Just yeah, so don't worry about it.
And also the, after this is the midterm, right? So it's
Yes.
like take home midterm or like compare and do it?
It's a midterm project. So I'll talk about it on Monday next week. And so basically you'll work on it for a month and then you're gonna submit. So basically the midterm project is gonna be like a finite element report. So I'm gonna give you a part, and unlike the activities, I'm not gonna tell you what to do with the part. And so you're gonna have to make all the decisions for like the meshing, for the boundary conditions, and then kind of justify all the decisions. You're gonna show me all the results and do the analysis on that too.
So you have a month to do that.
A month. Up until spring break.
Oh,
Oh, yeah, because I don't have time to.
Yep.
Yeah.
Oh, yeah, we also found out to do.
Hey,
I just had a question. So I tried to do part one, which was essentially like, so it was like probably in class that says be able to put in any number n, right?
Yeah.
So like this, I'm pretty sure looks right, right?
Okay.
Okay, but when I throw in like 100, I'm not sure if this is correct. So this is the one, this was the test one.
Yeah.
And should this go from negative, still go from 1 to -1?
Right, yeah,
Oh,
so,
so
so
I
as
messed
you, as you increase the amount of nodes, it should match this.
But this isn't right. 'Cause this should be not, this should be, it should still be, it's just like a lens, it's like more fine. It's
Exactly, so let's close this for a second. So I did see a couple of things. So the first thing that I noticed, so your grid spacing has to be.
Oh, that's not the right one.
Right, so the grid spacing has to depend on the number of nodes that you have.
Oh, that's right, that's right.
Right, so if you have, it works for 6 because we did 1 divided by 6 minus
Yeah.
1. That would, 0.2.
So this is, right, is that right?
Should be 1 divided by n minus 1.
Oh.
There you go. Sorry, again. I didn't really check down. There you go. So you can see that. From up there.
Oh, that's basically the fix.
Yes,
Seems to be.
it looks like it's still a little bit. So with the 100 nodes, they should match.
It should be matched, exactly.
Yeah,
Okay,
let's
so-
see down here.
Oh, would you wanna see, open it back up? I was having trouble because I was comparing the matrices between this one and the one in class.
Yeah.
And I was like confused by the boundaries because it showed like not the bottom right, not the most bottom right one, but the one to the left of that was like.
It was because it was the diagonals were 2, right?
Yeah.
And then everything to the left and right of them were negative or positive ones.
Yes,
But the bottom right most one, the one to the left of that was a -1, right?
that's because of the Neumann boundary condition.
That was which is not the set, that's the derivative basically.
Exactly. So I think
That's
the
what you
issue
with the coefficient,
issue is
right?
probably there.
Isn't that essentially what it is?
Yeah.
No, I see, I said it manually. Was that what we were supposed to do?
Yes,
I was
yeah.
in a hard.
Yeah. So for the boundary conditions, you can set them.
Yeah. I think,
This is Python, so yeah, so it starts at 0.
yeah,
That's
kinda
probably-
tricky. It's
it
actually the
is.
trickiest
It's really-
thing,
it's really
honestly.
tricky. Yeah,
trying to figure it out.
so for that, you would have. I think that's right.
This was also the same thing, I think, here. I kind of, what I did was, because on the first row, you don't want. It's a 1, the first row is a 1, not a 2, first row, first column.
Yes.
Because I put it to be all the diagonals to be 2, realized it was wrong.
Oh, okay.
And then I changed it. That's why this.
But
little
you're
one is just-
you're resetting it here anyway. and so I
Yeah,
think
more
this
time.
overwrites it.
Oh, you're right.
It's probably right. It could be, one thing that could be is that the Python lin solve right here.
Yeah,
Might be
Lin,
just a little bit different.
I can just try diagonal. Should be able to.
It should be the same.
Okay.
Well, you gotta sneak peek of Monday. That's an unstable solution.
That's cool.
I'll just switch it back. I mean,
Yeah.
I already had it before.
Well, it might be because I removed it. I thought like, I think they're doing the same thing. This one, these two lines and this line.
Yeah.
Because this is just saying if it's. Because if I don't add this, then it sets,
Okay.
it'll make the first one of the first row and first column be a 2, and I want it to be a 1.
One thing you could do, we did this kind of trick earlier today too, that you can change the bounds of the, so come back up here.
Up here, yeah.
And so instead of
That's
range
the
n,
tricky part,
you
yeah.
can do from 2 to n minus 1.
Yeah.
Then there's no, you know,
Okay. That, and then I
there's
can
no
just
ambiguity.
remove this, right?
Yeah, in theory, and then this
It-
one too.
Which one?
You need this one because it also sets the left, because this is for the, because it's -2 on the diagonal and then 1 on.
Yeah,
each
on
side.
the left.
So I think these two lines of code set
Okay.
that.
Oh, yeah, yeah. Yeah, oh, yeah, you are. Yeah.
So let's try. Oh, range, I think range might be the range. I don't think range kicks into it.
Oh, it doesn't?
But let's just do n.
Yeah, so.
I mean, it's basically there. I mean, it's probably just something really small. I wouldn't worry about it.
Okay.
It could just be a small thing.
Sure.
But yeah, it looks good.
Okay, cool. Oh,
Yeah.
thanks.
If last thing I would try is
Yeah, yeah.
instead of range n, try maybe range n minus 1, because then you don't mess with the.
Oh, yeah. I mean, like,
So it'll be the same.
I can always like use this, like make a numpy list space, but I'm trying to like use range because like I'm using Python. So
Right,
I
right.
want to use range.
Yeah,
I want to just use them, basically use MATLAB. So
Yeah.
I'm trying to get the hang of it.
It's mostly there. I think it's just something.
Yeah.
Send me the code and I can take a look tomorrow.
Okay, sure.
Yeah.
Thanks.
Mhm.